June 27, 1944. Lorient, France, the Kriegsmarine engineer, stood on the roof of Karaman 3, staring at a hole that shouldn't exist. 7 meters of reinforced concrete, 200,000 tons of roof slab. Calculations verified by Germany's finest structural engineers. All of it now punctured clean through, as if someone had driven a nail through butter. The mathematics had been perfect. The physics had been sound. But the hole was real, and 3 U-boats lay crushed beneath hundreds of tons of shattered concrete that had been designed to be impervious. Before we dive deeper into this story, if you're enjoying this journey through history, hit that like button and subscribe to stay updated with more untold stories from World War II. Drop a comment below telling us where you're watching from. We love hearing from our community around the globe. Now, let's continue. Standing there in the morning light, filtering through the dust, Corvette 10-caping helmet Bummerstedt realized something that would be repeated in engineering reports across the Reich within days. They had built fortresses to defeat yesterday's weapons, and the British had simply invented tomorrow's. The story begins not with bombs, but with coastline. On June 22, 1940, when France signed the armistice at Compiègne, Grand Admiral Dönitz saw what Winston Churchill desperately feared: 1,000 kilometers of Atlantic shoreline suddenly under German control. Before France fell, German U-boats operated from bases in Wilhelmshaven and Kiel, ports tucked deep in the Baltic and North Sea. Every patrol meant a brutal 7-day transit, just to reach the Atlantic hunting grounds where British convoys sailed. 7 days out, perhaps 10 days on station, if fuel allowed, 7 days back. The mathematics were crushing. A Type 7 U-boat spent more time traveling than actually sinking ships, and the Royal Navy's destroyers controlled every choke point around Scotland and through the English Channel. Then France fell, and overnight the equation transformed completely. Lorient, Saint-Nazaire, Brest, La Pallice, Bordeaux. These weren't just harbors, they sat directly on the Atlantic, shaving 2 weeks off every patrol cycle. A U-boat commander could now spend 3 weeks hunting convoys instead of 10 days. The operational efficiency gain was staggering, effectively tripling the Kriegsmarine's submarine presence in the Atlantic without building a single additional boat. Admiral Dönitz, commander of the U-boat fleet, moved his headquarters from Wilhelmshaven to the Villa Carillon in Lorient by September 1940. He understood that proximity to his operational boats meant faster tactical decisions, better coordination of Wolfpack attacks, and direct oversight of the campaign, strangling Britain's maritime lifeline. Every merchant ship Britain lost meant fewer tanks, aircraft, ammunition, and food reaching British soil. Britain imported 20 million tons of food annually, along with virtually all petroleum, rubber, and raw materials, keeping munitions factories running. By October 1940, the first flotillas were already operating from Lorient. Type 7 U-boats, pulled into French ports after patrols, underwent rapid maintenance and torpedo reloads, then headed straight back to the convoy routes. Turnaround time dropped from 6 weeks to 2. British merchant losses climbed from 200,000 tons in June 1942 over 350,000 tons by October. Dönitz was just getting started. But both Dönitz and Raeder recognized the vulnerability immediately. These Atlantic bases were now Germany's most precious naval assets, and the RAF would come hunting. The submarines needed somewhere bombproof to shelter, refit, and reload safely. The admirals needed protection, serious protection, because if Bomber Command destroyed the facilities or rendered the harbors unusable, every operational advantage evaporated. Organisation Todt mobilized 15,000 workers by February 1941. Fritz Todt himself approved the design's reinforced concrete structures engineered to withstand anything the RAF could drop. The specifications were extraordinary. Roof sections ranging from 3.5 meters thick at the thinner installations, to 7 meters at facilities like Karaman 3 in Lorient. 7 meters of steel-reinforced concrete. The engineers genuinely believed they were building structures that physics itself would defend. At Lorient, the Karaman complex eventually comprised 3 separate bunker facilities. Karaman 1 opened in February 1941 with 5 pens, each capable of sheltering a Type 7 U-boat before the concrete fully cured. Organisation Todt was already pouring foundations for Karaman 2, which added 7 more pens by October 1941. Karaman 3, the largest, wouldn't finish until January 1943. But when completed, it housed 13 pens under a roof slab weighing over 200,000 tons. St. Nazaire's submarine base matched Lorient's ambition. The complex featured 14 pens with roofs reaching 6.5 meters thick in sections. The individual pen chambers measured 15 meters wide and over 180 meters, long cavernous spaces where U-boats could dock entirely under cover. Maintenance crews worked beneath the concrete canopy, loading torpedoes and conducting repairs, while RAF bombers circled overhead, unable to touch them. The concrete itself represented a specific engineering calculation. Standard RAF bombs in 1941 were the 1,000-pound general purpose and 2,000-pound semi-armor-piercing variants. Both relied on explosive blast effect rather than penetration. German engineers calculated terminal velocities, explosive forces, and conducted tests against mock-up roof sections. Their mathematics showed that even a 2,000-pound bomb dropped from 6,000 meters would penetrate perhaps 1 meter into properly reinforced concrete before detonating. The blast would crater the surface certainly, but wouldn't compromise structural integrity. They added steel reinforcement in double layers. Horizontal rebar grids spaced every 30 centimeters throughout the concrete depth, with vertical reinforcement columns every 2 meters. The Germans thought of everything. By mid-1942, the bunker network was largely complete, and Dönitz's submarines had fortress protection. The admiral confidently predicted the RAF would exhaust itself trying to crack his concrete shields. Bomber Command was about to prove him correct, at least temporarily. Bomber Command sent 216 Wellingtons, Halifaxes, and Sterlings against Lorient on the night of January 13, 1943. The raid was the culmination of 18 months of increasingly desperate attacks against the U-boat pens. By dawn, reconnaissance photographs showed cratered dockyard facilities, destroyed warehouses, and the town of Lorient itself burning. But the submarine bunkers remained untouched. Not a single pen was out of operation. The attacks had started cautiously in 1941, with small formations dropping 1,000-pound general-purpose bombs. These weapons were essentially thin-cased cylinders filled with amatol explosive, designed to destroy buildings and infrastructure through blast effect. Against 5 meters of reinforced concrete, they were pathetic. Bombs struck the roof, detonated on impact, and gouged craters perhaps half a meter deep. Repair crews filled the holes with fresh concrete within days. Air Marshal Arthur Harris, appointed Commander-in-Chief of Bomber Command in February 1942, escalated the campaign. He authorized use of 2,000-pound semi-armor-piercing bombs, weapons with thicker cases designed to penetrate before exploding. The theory was sound. The hardened steel nose would bite into concrete. The bomb would penetrate deeper, and the delayed action fuse would trigger the explosion inside the structure rather than on the surface. Reality disappointed. The sap bombs penetrated perhaps 1 meter into the concrete before detonating, creating deeper craters but still nowhere near the 3 to 7 meters needed to breach the roofs. German engineers had calculated the safety margins correctly. The bombs simply lacked the kinetic energy and structural strength to punch through that much reinforced concrete. The cost was staggering. Between January 1942 and January 1943, Bomber Command flew over 3,000 sorties against the French U-boat bases. They lost 96 aircraft and over 600 aircrew killed or captured. The Germans lost not a single submarine to direct bombing inside the pens, not one. Wing Commander Guy Gibson participated in several attacks on Brest in early 1942. While commanding 106 Squadron, his combat reports reflect mounting frustration, accurate bombing runs, bombs observed striking the target area, then reconnaissance showing the pens undamaged and operational. The crews were risking their lives hitting a target they couldn't actually hurt. The Admiralty pushed Bomber Command relentlessly. Every U-boat sailing from those bases meant British merchant ships sinking in the Atlantic. In November 1942 alone, U-boats sank 119 Allied vessels, totaling over 700,000 tons. The pressure to destroy the bases was enormous. By spring 1943, senior RAF officers privately acknowledged conventional bombing couldn't crack the pens. The concrete was simply too thick and current weapons too light. Britain needed something revolutionary, a weapon operating on entirely different principles. Fortunately, one engineer had already started designing exactly that. Barnes-Wallis had already proven himself impossible to dismiss. On May 17, 1943, his bouncing bombs breached the Mchien and Edor dams in a single night, validating engineering calculations so precise that Air Ministry officials, who'd previously called him a dreamer, now hung on his every proposal. When Wallis suggested he could crack the U-boat pens, people listened. The Vickers-Armstrong engineer had been working on deep penetration bomb theory since 1941. His initial paper calculated that a 10-ton bomb dropped from 12,000 meters could penetrate 30 meters into Earth before exploding. The resulting underground detonation would create what Wallis termed a camouflet, essentially an earthquake effect that shattered structures through seismic shock waves rather than surface blast. The physics fascinated him. Conventional bombs relied on explosive force at or near the surface, creating pressure waves that dissipated rapidly in open air. Most energy wasted itself blasting atmosphere, but a bomb that penetrated deep before detonating would transmit shock waves through the surrounding medium with devastating efficiency. Wallis calculated that penetration depth depended on three critical factors: bomb, weight, impact velocity, and structural integrity of the casing. Standard bombs tumbled during descent, presenting variable cross-sections to the airstream and losing velocity. They struck targets at perhaps 240 meters per second. Their thin cases crumpled on impact, triggering the fuse before achieving deep penetration. His solution required rethinking the entire weapon. Make it streamlined, a perfect teardrop shape with stabilizing fins. Make it enormously heavy, construct the casing from special alloy steel, thick enough to survive tremendous impact forces without shattering. The numbers he calculated bordered on absurd. A 12,000-pound bomb dropped from 6,000 meters would strike the ground at over 340 meters per second, approaching the speed of sound. At that velocity, reinforced concrete behaved almost like a fluid. The bomb would penetrate by creating a temporary cavity as the material flowed around the weapon's streamlined body. Then came the earthquake effect. Once embedded deep in concrete, the bomb would detonate. Underground detonation trapped that energy, forcing it into the surrounding material. The shock wave would reflect off surfaces, creating standing waves that literally shook structures apart from inside. The Air Ministry remained skeptical. The Lancaster bomber's maximum bomb load was 14,000 pounds with modifications, meaning each aircraft could carry exactly one of Wallis's proposed weapons. Wallis countered with cold mathematics. Bomber Command had lost nearly 100 aircraft attacking the pens with conventional weapons. 0 results. His weapon needed perhaps 30 accurate hits, 30 sorties versus 3,000. The numbers spoke for themselves. Vickers-Armstrong received the production contract in September 1943. The casing demanded special treatment. Standard bomb-grade steel would shatter on impact at 340 meters per second. The Sheffield Works developed a chromolybdenum alloy hardened through heat treatment, creating casings that could withstand impact forces exceeding 15,000 pounds per square inch without fracturing. The bomb measured 6.4 meters from nose to tail fin. That teardrop shape was critical. Wind tunnel testing showed that even slight deviation from the calculated profile would cause tumbling during descent, destroying accuracy and drastically reducing penetration depth. For explosive fill, Wallis specified Torpex, a mixture of RDX, TNT, and powdered aluminum that was 50% more powerful than standard TNT. The Tallboy carried 5,200 pounds of Torpex, less than half the weapon's total weight. Wallis understood the physics. The casing's structural integrity mattered far more than explosive volume because penetration depth determined effectiveness. 617 Squadron received the Tallboy's wing commander, Leonard Cheshire, took command in November 1943 and revolutionized their tactics, developing low-level marking techniques where he'd dive to under 100 meters. Marked targets with flares despite intense anti-aircraft fire. Then high-flying Lancasters would bomb the marked point. This combination of courage and mathematical precision transformed what Tallboys could achieve. The raid on Lorient's Caramon pens launched on June 27, 1944, 3 weeks after D-Day. Cheshire led 16 Lancaster bombers from 617 Squadron, each carrying a single Tallboy. German forces were reeling from the Normandy invasion. Air defenses stretched thin, and the U-boat pens had become critical as Allied naval forces tightened their grip. Cheshire took off first in his Mosquito. He crossed the French coast at 200 meters, hedge-hopping to avoid radar. He identified Karaman 3, the massive complex with 13 pens and that 7-meter-thick roof that had laughed at hundreds of previous raids. He pulled into a shallow dive, accelerated to over 500 kilometers per hour, and released his red target indicators directly onto the bunker's roof, while 88mm flak batteries tracked him. 6,000 meters above, the Lancasters watched the red smoke billow. Flight Lieutenant John Cockshott steadied his bomber. The bomb aimer called corrections, and at precisely the calculated release point, the Tallboy dropped away. The weapon fell for 43 seconds. Impact velocity exceeded 340 meters per second, over 1,200 kilometers per hour. The Tallboy struck Karaman 3's roof approximately 6 meters from Cheshire's smoke markers. What happened next stunned German engineers. The bomb didn't bounce or shatter. It punched through 7 meters of reinforced concrete as though the material was packed sand. The penetration lasted perhaps 0.2 of a second. Then the delayed fuse fired. 5,200 pounds of Torpax detonated inside the concrete roof slab. The explosion couldn't escape. 7 meters of concrete trapped the blast. Instead, energy transmitted through the structure as a compression wave traveling at over 5,000 meters per second. The shock wave reflected off surfaces and created standing interference, patterns that literally vibrated the concrete, apart from inside. A section 20 meters across collapsed catastrophically, dropping hundreds of tons of shattered concrete into the pen below. 2 Type 7 U-boats were crushed instantly. A third sustained damage so severe it would never sail again. 14 more Tallboys followed. Not all struck the roof directly, but those near misses proved Wallis's earthquake theory spectacularly. The bombs buried themselves 6 to 8 meters into earth before exploding, sending shockwaves rippling through the ground that cracked the bunker's foundation walls. By the time the last Lancaster turned for home, reconnaissance photographs showed Karaman 3 with multiple roof breaches, collapsed internal structures, and damage the Germans had considered physically impossible. Corvettin-capping Bummerstidt's technical assessment noted that conventional bomb craters typically measured 1 to 1.5 meters maximum depth. These Tallboy impacts showed smooth penetration channels extending far deeper. With explosive detonation occurring entirely inside the structural mass, the damage mechanism was unlike anything they'd encountered. St. Nazaire received 617 Squadron's attention on August 9, 1944. 19 Lancasters delivered their Tallboys with precision that horrified the German garrison. 4 bombs achieved direct roof penetration. One struck the massive seaward blast door and punched completely through 3 meters of armored steel before exploding. Inside the door was torn from its hinges and twisted into scrap. Brest's turn came on August 6th with similar results. 3 separate roof breaches collapsed sidewalls in 2 pens, and the rail-mounted crane system destroyed beyond repair. German damage assessments calculated 4 to 6 months minimum repair time. What terrified Dönitz was the efficiency. Bomber Command wasn't carpet bombing anymore. 617 Squadron was conducting surgical strikes with weapons purpose designed to defeat reinforced concrete. By mid-August 1944, every major U-boat bunker on the French Atlantic coast had sustained significant damage. The invulnerability was gone. Dönitz faced a crisis. By September 1944, his Atlantic bases had transformed from force multipliers into operational liabilities. U-boats couldn't risk extended stays in damaged pens. Rapid turnaround times evaporated as submarines dispersed to improvised facilities. A Type 7 U-boat in mid-1943 spent 10 days in port between patrols. By late 1944, turnaround time averaged 23 days. Dönitz was losing half his operational force to maintenance delays caused by Tallboy-induced infrastructure destruction. The strategic timing amplified the disaster. By late 1944, Allied escort carriers, improved sonar, and airborne radar had already tilted the Atlantic battle against U-boats. The period historians call Black May of 1943, when Dönitz lost 43 submarines in a single month, had forced tactical retreats. British merchant ship losses reflected the shift dramatically. In 1942, U-boats sank over 7.8 million tons of Allied shipping. By the final quarter of 1944, monthly losses had collapsed to under 80,000 tons. The Tallboy raids represented something unprecedented. the deliberate application of physics to defeat a specific defensive technology. Previous bombing doctrine relied on overwhelming volume. Barnes-Wallis demonstrated that understanding vulnerabilities could achieve with 30 sorties what 3,000 CONVENTIONAL raids couldn't accomplish. Post-war analysis revealed fascinating details. At Karaman 3, engineers excavated Tallboy impact sites and measured actual penetration depths against Wallis's calculations. The correlation was remarkable. Predicted depths matched observed depths within 15 centimeters. The man's mathematics had been essentially perfect. The U-boat pens at Lorient still stand today. Tourists walk through cavernous chambers where submarines once sheltered, staring at roof sections bearing Tallboy impact scars, smooth penetration holes that drove clean through what was supposed to be impenetrable. The story isn't really about bombs or concrete. It's about the moment when certainty shatters. The German engineers had done everything right by the standards of their time. Their mathematics was flawless, their concrete perfectly poured. They had simply assumed the future would fight with the past's weapons, and Barnes-Wallis had asked a different question entirely. What if we stopped trying to blast through concrete and instead taught bombs to swim through it like water, then explode from inside, where physics becomes inescapable?